Welcome back. So we're having a discussion about the time invariant system. We had introduced to the formal definition, which read that if I have a system, I'm giving some input, it gives me some output. Now, for the same system, if I am shifting my input, whether through the time delay or time advance, then if the system is time invariant, then the shift should be preserved in the sense that the same amount shift should appear in the output as well. Fine. Now, if you remember when we did the introduction to systems, we had kind of represented that shift operation by something like this. I hope you remember it, that I have a system H is equivalent to S superscript K. So it basically meant if I'm giving an input signal X of t, my output will be Y of t X of t minus K. It will be shifted by that amount. Fine. So let's try to analyze the time invariant system in terms of this. So what I will do is we'll take a simple continuous time system which is represented by the which is our general expression y of t is equivalent to h of x of t, some transformation on the input signal x of t. So x of t here is the input signal and y of t is the response of the system to this signal x of t. Now if I have a second input, fine, so if I have another input which is shifted in time, say I have x of t minus t naught, fine, and this is basically s of t naught acting on x of t. Fine, you have a signal x of t like I have drawn graphically here, x of t. You're using this signal as an input to a system, to a time delay system s superscript k. So it is producing an output with that amount of delay. Same thing I have expressed it mathematically. Sorry. Fine. And here the operator s superscript t naught, it is basically a time shift operator. Its shift is by that amount. Fine. Now if I want to see the output, so let me call it y subscript I want to see what is the output of this system that is defined by h to this time shifted input. Right? So I can write it as h for x of t minus t naught. I can write it in terms of the shift operator s superscript t naught acting upon x of t. Fine. Then I can take these two operators, h operator and the shift operator outside. So in combination, these two operators act upon x of t. Fine. So graphically, it is something like this. What I have done mathematically here, it means I have two systems. I'm using my input x of t to the first system, which basically provides a shift of t naught. So this right here is xt minus t naught. Then I am using this shifted signal to the system, having the system property h. It gives me an output y of t. Right? This is the first part of the analysis. Now let us suppose, so let y subscript to o t, it represents the output of the original system, that is h, shifted in time by t naught units of time. Okay. In other words, what I'm saying here is I have defined y subscript o of t as s superscript t naught acting upon my conventional output y of t, which is this. Fine. So again, I can do some substitution. So this is shift operator y of t. I can simply express it as h of x of t. and I can take the operators outside S. This is the shift operator, then the system operator H acting upon X of t. Now graphically it is something like this. I have first operator H. I am giving my input signal X of t. It is giving me my output Y of t. Then on this output I am basically applying the shift operator T naught, and it gives me Y O t. Now if this system is time invariant, then these two outputs should be same. And this is basically the crux of the thing, that if this system is time invariant, then these two outputs Y I T should be equal. Okay. Yeah, you can say the sequence of the operators, it should not matter, because if you look closely, what I am doing in the first case, I am first providing a shift, then I am using the operator H, whatever the operator H is. Then in the second case, I am first providing this transformation H, then I am shifting, right? So in other words, if you are in these two operators, we say this basically means that H and ST naught, they should be commutative. So the order does not matter. It does not matter whether you first provide the shifting operation, whether you first do the actual transformation, it does not matter. So we say the system is time invariant. Right? So this was a bit of an analysis. We try to look at the same thing through a different angle in terms of this shifting operator and a normal transformation that the system is doing on the input, right? So in that regard, turns out that a time invariant system, the shifting and the actual transformation that the system, these two operators, they should be commutative, that their order does not matter. In case it is time variant, then they're not commutative. The order will matter. So it will change the output, and the output will depend upon whether you are first performing the shift operation or whether you are first performing the actual transformation. Fine. Yet again, a very important property, time invariance property. Then finally, we have the property of what you call stability. Right? Stability is defined in different disciplines. You will learn about stability in electronics as well, when you will do some transistor amplifiers. You will also learn about stability. In fact, your entire control system is basically revolving around the stability of the systems, right? Here we also have a concept of stability and an in-depth concept of stability, but it is slightly different the way we define this system stability in this course. So it is in terms of, like, see, everything we have done so far is in terms of inputs and outputs. Starting from the definition of system itself, it was in terms of input and output, X of t being the input, Y of t being the output. Then we had the transformation H, right? So even proper linearity, again, it was based on input. Linear weighted combination of input should provide a weighted combination of outputs. Again, it was input. Causality, again, it was in terms of inputs. If your output depends upon present and previous samples, it is causal. Similarly, stability, the definition we use here is in terms of input and output. So the way we define stability here is that a system is said to be, we use a particular kind of stability criteria here, is said to be bounded input, bounded output. So we sometimes use the acronym BIBO, BIBO, bounded input, bounded output, stable. It means I'm giving a bounded input. Bounded input means I'm giving a finite input, which is not infinite. It has some finite value, right? like your sinusoidal wave, it is a finite signal. It does not shoot to infinity. It fluctuates between +1 and -1. So it is a bounded input. Now, the concept is simple. You have a system and you are giving a bounded input to your system. And if the output is also bounded, means it converges, it has a finite value, it does not diverge, then we say the system is stable. Right? So let me complete it. A system is said to be bounded input, bounded output, or be both stable if and only if every bounded input results in a bounded output. Fine. So you're given some finite input and you're getting a finite output. Right? So again, we can do a bit of mathematical analysis that will help us later. So I have a continuous time system. Y of t is equivalent to h of x of t, and we have to see whether this system represented by the system function operator h, whether this is stable or not. So it is something like this, that if I am giving, so this is my system, if the input is bounded. Now mathematically how we represent a bounded input is something like this, that magnitude of x of t, it is less than equivalent to some value m of x which is less than infinity for all values of t. Fine. And you are giving this kind of input, and when you give this type input, जो आपका output है, it should satisfy this, that the magnitude of the output should be equivalent to some value, say m subscript y, which should be less than infinity for all time. Right? And these two, mx and m subscript y, they represent some finite quantities. Fine. So this is the definition of stability here. So this is the last property that we will be discussing regarding the system. So we have done 6 properties. Out of these 6 properties, the important ones are linearity, time invariant, causality, and stability. And you will see our further discussions that we will do. It will be basically revolving around these properties. We will be tackling these properties through different scenarios, using impulse response, using differential equations, then in the frequency domain using the Laplace transform, using the Fourier transform, and using the Z transform. But it will be revolving around these properties. Okay? So we'll stop here. I will add one more video. We will do some analysis so that you kind of get prepared for it. Then we will have a real-time interaction in the coming weeks.